In the previous class, we studied about the uh, universal gates. Universal gates. Okay. Universal. What are universal gates? NAND and NOR gates. Okay. Both NAND gate and NOR gates are known as universal gates. Okay. What is the meaning of universal gates? What do you mean by saying universal gates? Any other gate. What are the other gates? What are the other gates? AND gate, OR gate, NOT gate. These three are basic gates. Then also there are few other derived gates. What are the derived gates? Very good. XOR gate, NAND gate, NOR gate, XNOR gate. These are all derived gates. By combining two basic gates, we produce other new logic gates. Okay. As you know, logic gate is used to take decision. So in order to make any decision or in order to make any automated system, we have to design a combinational logic circuit with the help of these gates. So in order to construct a combination logic gates, if we use universal gates, it will be easier for us to construct the circuit. That with few examples we saw in the previous class. Because in the case of XOR gate, actually we needed 5 different gates, but when we use these NAND gates, only 4 gates were required to construct an XOR gate. Also, when you make an AND or combinational logic circuit, instead of going for different types of circuits, gates, different types of gates. For example, we need AND gate, OR gate, sometimes NOT gate. So we have to combine all these gates. These gates are available as integrated circuits. So we need different types of integrated circuits. So when you use more integrated circuit, more ICs, it will consume more power. So instead of that, if we can convert the same circuit with the same functionality with the help of these universal gates, it is sufficient for us to use 1 or 2 chips, 1 or 2 ICs. So power consumption also will be reduced. Also the heat produced in the circuit will be reduced. Cost of the construction, cost of the circuit also will be reduced. So these merits are there. Okay. Now let us see the second universal gate, which is NOR gate. How NOR gate can be used to construct all other gates. Okay. As you see, these two are the universal gates. This is a NOR gate. Suppose you say this is input A and this is input B, then generally we label the output as Y. So in this case, Y is equal to A plus B whole bar. A plus B whole bar. Okay. So if you know this large Boolean equation for this particular function, NOR function, it is easy for you to make the truth table. Because what is a truth table? It's a table consists of all the truth functions. All possible input combinations are listed in the table. Okay. So we can make our table. Easily we can make the truth table for this particular function. So what are the possible combinations? We have 2 inputs, A and B. So both inputs can be false or both inputs can be put as 0. So 0, 0 input. When the inputs are 0 and 0, then in an OR gate, what will be the output? 0 plus 0 is 0 plus 0 is 1. 0 plus 0 is 0. 0 bar is 1. So we get 1. Then A is 0 and B is 1. In this case, what is 0 plus 1? 1. So 1 bar is 0. In the case of 1 and 0, 0. When both the inputs are true, 1, 1, then 0. Okay. So this is the truth table. This is the truth. This is called truth table, right? Because it gives the truth function. Truth table of NOR gate. Now this NOR gate can be used as universal gate. That means using this NOR gate we can construct all sorts of other gates. That means any combinational logic circuit can be constructed. That's the meaning. Any combination logic circuit can be constructed by using only NOR gates. No other gate is required to construct any combinational logic circuit. Okay. So that is the advantage of studying this universal gates. Okay. Now first case, simplest case, NOT gate. Okay. For NOT gate, we need only one NOR gate. Both the inputs are tied together. A and B are tied together. We have given the common label A. Okay. Now the output, what will be the output here? Output, suppose you call this output as Y as usual, then Y is equal to A plus A bar, right? Because A and B are the usual inputs. Now we have put the same input for both the input terminals, so the input becomes A plus A. So A plus A bar. What is A plus A? A plus A is A. So it becomes A bar. Therefore, we can say the output is not A. Therefore, this simple arrangement, with this simple arrangement, a NOR gate can be easily converted into a NOT gate. Okay. Then let us, this is the snapshot of the simulated output. The result shows that when the input is high, then the output is low. When the input is low, the output is high, and when input is high, then output becomes low. Just complements. Okay. How we can construct an OR gate? What is an OR function? This particular gate produces NOR output. What is NOR? Negative OR. When you negate the OR output, the output of an OR gate, when the output of an OR gate is negated, it produces NOR gate. So in the same way, when we make another inversion, double inversion, then we will get back the OR function. So this NOR gate produces inverted OR output. So again we invert it. So it becomes double inversion. So we get OR operation, OR output. Okay. If A and B are the inputs, then the output of the first NOR gate will be A plus B bar. Then this particular unit, as you know, from the previous slide, this arrangement is simply NOT arrangement. Okay. So this is a negate inversion function, inversion operation or NOT operation. So it is again inverted. So we have double inversion. So A plus B with the double bar becomes A plus B. Okay. These two will, because A bar whole bar is equal to A, or A double bar is equal to A, or we can say A double prime, that way also you can say. Okay. So this particular arrangement gives OR output. Instead of constructing the circuit, now we have this simulation. We can visualize the input output conditions using this simulated circuit. We have input A and input B. Okay. Let us make input A and B 0, then output has become 0. You make input A high, A 1, then you get out, because 1 plus 0 is 1. Okay. Then you make B high, again you get 0 plus 1. Okay. Therefore we have high output. When both inputs are made high, 1 plus 1 is again, in a Boolean logic algebra, 1 plus 1 is 1. Therefore you get the actual OR output using this combination. Okay. So only in this case we have, only for 0 0 we get the false output, 0 output. Okay. So this particular arrangement functions as an OR gate. These are the snapshots of the various input output conditions. Then AND gate. What is an AND gate? AND gate, what is AND logic? AND gate produces true output only when all its inputs are true. So for an AND gate, the output should be true only if all its inputs are true. If any one input fails, if any one of the input is false, then the output should be false. Okay, that is the AND operation. Now let us take this circuit. is a kind of combinational circuit, right? We have combined three NOR gates. Here this final output is nothing but AND output. As you look at this board, you may not see AND operation there. But we know De Morgan's law. We know De Morgan's law. When you apply De Morgan's law, that will show you that it is nothing but A dot B. Okay. Now we provide here input here A, and A becomes A bar. Input here B, and B becomes B bar. Now A bar and B bar are fed to the third NOR gate. So third NOR gate output is A bar plus B bar whole bar, right? It doesn't look like AND, but when you apply De Morgan's law, what will you see? What will you do? You will cut it here. I have told you the shortcut. Cut the line, change the sign. Change the sign means you have to make plus into dot and dot into plus like that. So this will become A bar dot B bar, then we have to cut the line. So it becomes A dot B, or it is equal to A and B. Okay. So we have construct AND gate with the help of three NOR gates, right? This can be experimentally verified, or we can run a simulation and verify this circuit. For 0, 0, we get 0 output. Then A is equal to 0 and B is equal to 1. Again we get 0. Then A is equal to 1 and B equal to 0. Again we get 0. When both are made true, or 1, 1, it gives 1. Okay. So when both the inputs are true, then the output is true. So it's a 2 input AND gate. We can have multiple inputs. 5 input AND gate means all the 5 input must be true in order to produce a true output. Okay. This is the snapshot of the output. Then NAND gate. Once we constructed an AND gate, it is easier for us to produce an AND gate. What is an AND gate? Negative AND. So already we have the AND gate with us. Now you compare this circuit with the previous circuit. This is the AND gate. This produces AND output. Okay. So only thing we have to negate this output. So we have to add a NOT gate at the output terminal, and we have added the NOT gate. NOT gate, already we know how to construct a NOT gate with the help of the NOR gate. So NOR gate, when both the inputs are tied together, it acts as a NOT gate. So we have made the NAND from the previously constructed AND. So the output of the AND is negated and we get the NAND. Okay. So we can construct a NAND gate with the help of the NOR gate. Totally we need 4 NOR gates to construct one NAND gate. Okay. Okay, you put 0, 0 input. In an AND gate you will get, for 0, 0, the output will be 0 in the case of AND gate. Now it is negative AND gate, that's an AND gate. So therefore it will produce high output. In the case of 0 and 1, A is 0 and B is equal to 1. You have high output. Then A is equal to B equal to 0, A equal to 1. Again you get output when A and B are true. Okay, you get the high output. This is the snapshot of the outputs available, simulated using another software. So we get a 0 and 1 like this here. Then finally XOR gate. XOR gate. In the topic that we have covered so far, XOR gate is the gate which is a bit more complicated. Means it has a combinational circuit with the 2 different and operations, two different and expressions combined by an OR expression. So it is a and OR expression by itself. A simple XOR gate itself has AND OR combination. So it is an AND OR combinational circuit, right? Because what do you mean by A XOR B? A XOR B is equal to A B bar plus A bar B. So that itself is having two different AND expressions combined by an OR expression, right? So in the case of circuit construction also, definitely it will have more, it will involve more number of gates, okay? Because XOR function is like this. Y is equal to, when you say Y is equal to A XOR B, that implies A B bar plus A bar B. There are two AND terms combined by an OR term. So in normal circuit construction, suppose we want to construct an XOR gate, you may require an AND here, another AND here, OR here, then two NOT gates. So that construction itself will be like this. Suppose you want to construct a circuit for this, then the circuit will be like this. An AND gate, another AND gate, these two outputs then fed to an OR gate, right? Then for this input also we have to negate the one of the inputs, okay? So we have to negate it. That means suppose we give A here, we can connect, what happened? We can connect the A to this point. Again, suppose this is B. Okay. So this A and this B will be inverted here. So you have this A here, so it is inverted here, A bar. Therefore, this particular, the first AND gate will produce the A B bar, and this will produce A bar B. Therefore, this final output, it is simply OR operation. So it will combine, or it will OR these two outputs. Therefore, this Y here will be equal to A B bar plus A bar B, which is nothing but A XOR B. So whenever we say A XOR B, it appears as if it is a very simple operation. But that A XOR B operation itself has this type of complexity. It is a combinational logic circuit comprising of two different AND expressions. And in the two different AND expressions, we have two NOT operations also. So if we count all these, 1, 2, 3, 4, 5, we require 5 gates. Here in this case also we have 1, 2, 3, 4, 5 gates. Okay. But here all the gates are NOR gates. Here we need three different types of gates. We need a NOT gate, AND gate, OR gate. So you require three integrated chips, three ICs in a board. But in this case, 4 gates are normally available in one chip. So you require only two integrated circuit, two chips. With two ICs, we can construct this circuit. Okay. Now let us see whether this operation will be working perfectly. Okay, let us look at these snapshots. Here we have, in the first box we have 0, 0 input. A and B both are zeros. So the output is 0. This is the truth table. This is how the XOR function, XOR operation functions. So 0, 0, for 0, 0 input we have 0 as output. When 0, 1 is given as the input, then the output becomes 1. Then for 1, 0 input, again the output is 1. In the case of 1, 1 input, this is the peculiar input condition which differentiate this XOR gate from ordinary OR gate. In ordinary OR gate, when both inputs are true, then the output will be naturally true. But in the XOR gate, the output will be false even if two inputs are true. Okay. So this particular gate, XOR gate, can be used as parity generated, parity checker. You can use this XOR gate to verify whether even number of high true states or high states are available in a string of information, string of data. So suppose we have 7-bit data, we can feed all the 7-bit information to the 7 input XOR gate. Then the output, if the output is true, then that means we have odd number of true inputs. Okay, like that. So we can check the parity. So this can be used as a parity checker. Also we can use it to generate parity. So for data transmission, this XOR gate will be very much useful. Also in the case of construction of arithmetic circuits, maybe adder circuits, half adders, full adders, we make use of the XOR gate. Okay, in a half adder circuit, how many XOR gates are implied? You are doing it in the laboratory. Okay, in the laboratory practicals, you are doing half adder. How many XOR gates are implied in one half adder? Two XOR gates for half adder. Only one XOR gate is used. Only one. How many AND gates are used? Only one AND gate is used. For half adder operation, for half adder you require only one AND gate and one XOR gate. Okay. What is an half adder? It's an arithmetic adder which gets two inputs and produces two outputs. So A and B, only two inputs are fed to the half adder, and the outputs are known as sum and carry. Okay. For producing sum and carry, we use only an XOR gate and AND gate. So only one gate is required. The same can be executed with the help of these NAND gates or NOR gates. If you don't have other gates, we can do it. But in that particular circuit, it may require more number of gates than the simple usage of an XOR gate and AND gate. Okay. So any questions? So you are clear with the topic. Okay. Thank you.